Now we are going to talk about de Broglie, Louis de Broglie. That's his photo. Um, Now, what he did, what he did was he learned about the photoelectric effect, and in university, and what he did was he tried to think that if light, which is a wave, can behave like a particle, okay, how about particles behaving like waves? Okay, so he did all his experiment and he proved it. Okay, now I show you how does he proved it. The idea is if you show well, let's try to do this. Okay, now on your notes, page 12.3, here is a picture of diffractions. On the right hand side is the diffraction of X-rays through a small slit. On the right hand side are the diffractions of electrons. So the idea is if we can project electrons at a very fast speed, okay, and it behave like waves. Okay. Remember, diffraction only occurs when for waves. Okay. Diffraction is a property of waves. So particles doesn't diffract from classical physics. So the idea is if I throw a basketball through a gate or a door, the basketball is going to travel straight. Okay. The basketball is not going to bend because it went through a slit. However, electron did. And yes, they did. Yep. Okay. Now, here is the calculation of it. Okay. So, what you have to know is the momentum. What I discovered was the momentum of the photon is h Planck's constant divided by the wavelength. Yeah, if you know the wavelength of the photon, you are able to find the momentum of it. And the momentum is basically mass times velocity. So mass times velocity equals to h divided by its wavelength. Okay. Then he rearranged this equation. So wavelength is basically Planck's constant h divided by mass divided by its velocity. Okay. So from his calculation, he can find a wavelength, okay, of all the moving particles. Okay. Basically, the wavelength of all the moving objects. Okay. Now, let me show you an example of it. Here. Okay. Now, for question 1, okay, we have an electron of this mass moving at this speed. Okay, so if I do it, so what we can do is if we apply de Broglie's equation, we can find its wavelength. Okay, so Planck constant is, so what we need to do is we just need to put in all the numbers. Planck constant is, let me change color, 6.6 times 10 to the power of minus 34, okay, divided by the mass of the electron, okay, then divided by its velocity, which is here. Then we find a number in meters. Okay, if you type the number in your calculator, you find this number. Okay, so what de Broglie told me is, from this equation, an electron moving at this speed will behave exactly like a wave with a wavelength of 4.8 times 10 power of minus 10 meters. So when it goes through a slit that is smaller or equal to this wavelength, okay, diffraction occurs. Okay. And by the way, this is basically the wavelength of X-rays, and he compared the diffraction of X-rays in that single slit experiment. Then he concluded that electrons do behave like waves when moving at a certain speed. Yep, that's basically it. Okay, but if we look at question B, okay, now just remember from de Broglie, de Broglie, his name is de Broglie, but yeah, he's a French scientist. Just a lot of, well, I don't speak French, so when I learned physics, my teacher told me his name is de Broglie, but it's de Broglie in French. Anyway, from his equation, he told me we can find the wavelength of basically every moving object. So if I do the same calculation when a marble of this mass moving at 6 meters per second, okay, so if I put the number in, okay, by the way, you can do the calculation too. I have 2.2 times 10 to the power of minus 33 meters. Okay. So a marble moving at 6 meters per second behave like a wave of a wavelength of 2.2 times 10 power of minus 33 meters. Note that it's a very, very small number. Okay, so what his explanation was, okay, when a marble travels along, if I have a marble, it travels along. Okay. We say it travels along like that. Okay. But actually, the marble, as it travels along, it vibrates up and down. Okay, and with an amplitude. Okay. But well, let's draw it this way. Okay, so basically, the marble travels along, okay, like this, with a wavy shape. Okay. Since the wavelength is too small, okay, we are not be able to say it. Remember, this is a really, really small number. So that's what his formula tells us. Okay, so in order for the marble to be diffracted when it travels through a slit, okay, the slit has to be less, okay, or at least equal to this distance. Okay. Of course, when we find a slit that is so small, the marble cannot travel through it because the marble has to be bigger than this. So that's the reason why when we throw basketball when the basketball is through a door, okay, we never say it deflects, or we never say it diffracts, because it travels as a wave, okay, with a very small wavelength, and the door, the width of the door must be like billions, trillions times bigger, so diffraction does not occur.